Hang on, I'm getting the recording going and then we'll begin. All right, hello everyone. Thank y'all for showing up to class today. Again, my discussions keep getting smaller and smaller, but with this weather, I somewhat understand. But yeah, so we are going to finish our last discussion before exam 3. So there's only 2 discussion worksheets on this exam. So definitely you're going to want to put your study focus into the material and lecture, and then just a little bit on what we've done in discussion. But today it's discussion 8, and we will be looking at the baroreflex. So before we hop into the questions, let's go ahead and just discuss what a baroreflex is. So the baroreflex is how our body maintains blood pressure. So if you've ever heard of like a barometer before, that's like this instrument that determines like, atmospheric pressure, things like that. Same thing here, except we're looking at our internal body pressure. So it works through negative feedback. So we'll look at some examples of how that happens, but just know for now that it is going to work through negative feedback. And if you remember, negative feedback is going to kind of cause an inverse reaction. So if we have high blood pressure, it's going to work through baroreceptors to kind of release or decrease that high blood pressure. So baroreflex works through the baroreceptors. So baroreflex is the actual function, but it does that through baroreceptors, and we find them on the aorta and the carotid artery. So we know now that the aorta is the biggest vessel that comes out of the heart. It's about as thick around as a water hose, so it stretches and constricts quite a lot. And then the carotid artery runs in the neck. So the one that if you ever like are trying to determine your heart rate, you kind of like palpate that with your fingers. That's the carotid artery. So baroreceptors are a type of stretch receptors. So they work through mechanical stimulation. So whenever they detect a stretch or detect, shrink, that's how they work. So for example, if there's more stretch in the aorta or carotid artery, there's going to be more cardiovascular control center activation. So CVCC means cardiovascular control center. So just like we have the neural control center, we also have the cardiovascular control center. So when we have more cardiovascular control activation, we'll have more PSNS activity, so more rest or digest activity. And this will lead to a decrease in blood pressure. So there's a couple connections to make here. Of course, more stretch, if it's being stretched more, that means we're gonna have a higher blood pressure. So if we have more pressure, that vessel is gonna start, stretching more. Whenever that's happening, we want to bring that blood pressure back to normal. So more stretch, we need to decrease blood pressure. More stretch, we need to increase PSNS activity so we don't release epinephrine and norepinephrine, causing it to beat too hard. So yeah, one other thing to note is that the cardiovascular control center is located in the medulla oblongata. So just in case you didn't know that, it's in the brainstem there in the medulla. All right, so what we see is that the cardiovascular control center is innervated by both the parasympathetic nervous system and the sympathetic nervous system. So this is super important to know, and this is a question, but this is kind of a preview of it. But what we see is that the parasympathetic nervous system is only going to innervate the SA node. The sympathetic nervous system innervates the SA node as well as the AV node. Those contractile cells at the heart that we looked at last week that actually cause the contraction of the heart, and also some blood vessels, specifically the arterioles and veins. So the SNS innervates quite a lot compared to the PSNS, which only innervates the SA node. So it would work by innervating that SA node whenever we are in rest and digest, which would decrease our heart rate. It does that by releasing acetylcholine to the pacemaker cells in the SA node. And we know that those are those muscarinic receptors. Give y'all a second to record. Cool. So when looking at an example of a baroreflex, what we can think of is what would happen if a patient's blood pressure decreases and they pass out, or sometimes it's not as severe as passing out, they become lightheaded or just a little fatigued. But that's what normally occurs with a major blood pressure decrease, fainting. So how our body would respond to this is the sympathetic nervous system would pick up that we have super low blood pressure, and it would activate that cardiovascular control center. It would decrease PSNS activity as well, because these normally will not be activated at the same time. So when we activate our cardiovascular control center by that SNS, heart rate will increase, and so will the contractility. Lastly, and it is important to note that the baroreceptors are last in line, but what we see is that they will become activated and cause the vessels to constrict to raise that blood pressure back to normal. So our blood pressure decreases. That's normally going to mean our vessels are going to be pretty dilated. There's not a lot of pressure. You can kind of think of that relationship. I think it's like Boyle's law: increase in pressure, inverse decrease in volume. So that's kind of an inverse of each other, pressure and volume. So if we have more pressure, we're going to have a decrease in volume. If we have less pressure, we're going to have an increase in volume. So kind of just think of those. So if we have decreased pressure, we're going to have increased volume, or area. And therefore, our SNS is going to pick up on that and say, okay, we don't have enough pressure in our vessels. We need to do something about this. So it'll activate that cardiovascular control center, increase heart rate, so increase pressure. And then those baroreceptors will cause the vasoconstriction of those vessels, which will, shrink that space, and we'll start sending blood back to the heart quicker. All righty. So here's just a quick video that we can watch to kind of see what's going on here before we hop on into the actual questions.
Baroreflex, or baroreceptor reflex, is one of the mechanisms the body uses to maintain stable blood pressure levels, or homeostasis. Baroreflex is a rapid negative feedback loop in which an elevated blood pressure causes heart rate and hence blood pressure to decrease. Reversely, a decrease in blood pressure leads to an increased heart rate, returning blood pressure to normal levels. The reflex starts with specialized neurons called baroreceptors. These are stretch receptors located in the wall of the aortic arch and carotid sinus. Increased blood pressure stretches the wall of the aorta and carotid arteries, causing baroreceptors to fire action potentials at a higher than normal rate. These increased activities are sent via the vagus and glossopharyngeal nerves to the nucleus of the tractus solitarius, the NTS, in the brainstem. In response to increased baroreceptor impulses, the NTS activates the parasympathetic system, the PSNS, and inhibits the sympathetic system, the SNS. As the PSNS and SNS have opposing effects on blood pressures, PSNS activation and SNS inhibition work together in the same direction to maximize blood pressure reduction. Parasympathetic stimulation decreases heart rate by releasing acetylcholine, which acts on the pacemaker cells of the SA node. Inhibition of the sympathetic division decreases heart rate, stroke volume, and at the same time causes vasodilation of blood vessels. Together, these events rapidly bring down blood pressure levels back to normal. When a person has a sudden drop in blood pressure, for example, when standing up, the decreased blood pressure is sensed by baroreceptors as a decrease in tension. Baroreceptors fire at a lower than normal rate, and the information is again transmitted to the NTS. The NTS reacts by inhibiting parasympathetic and activating sympathetic activities. The sympathetic system releases norepinephrine, which acts on the SA node to increase heart rate, on cardiac myocytes to increase stroke volume, and on smooth muscle cells of blood vessels to cause vasoconstriction. Together, these events rapidly bring up blood pressure levels back to normal. Baroreflex is a short-term response to sudden changes of blood pressure resulting from everyday activities and emotional states. If hypertension or hypotension persists for a long period of time, the baroreceptors will reset to the new normal levels. In hypertensive patients, for example, baroreflex mechanism is adjusted to a
Okay, we don't need to look at hypertension, but yeah, that's just a good little visual that I wanted to include in case you needed to kind of see it, just because reflexes and receptors are kind of hard to picture in your head. But yeah, so now let's hop into our actual questions. So this should be the first chart on your discussion worksheet. So what we're going to look at is kind of what we just talked about when looking at low blood pressure and high blood pressure. So with low blood pressure, our baroreceptor firing rate will be decreased. So remember, it works through negative feedback, so it has kind of that inverse action. So with low blood pressure, we have a decreased firing rate from those baroreceptors. A decreased firing rate from the baroreceptors is going to cause an increase in sympathetic output, and we will also see a decrease in parasympathetic output. So low blood pressure is going to trigger our fight or flight and decrease our rest and digest, all because of those baroreceptors. High blood pressure is going to increase the baroreceptor firing rate, and this will cause a decrease in sympathetic output and an increase in parasympathetic output. So high blood pressure is going to kind of signal that rest and digest. Our blood pressure is high, our body is telling us, hey, we need to slow down, we need to calm down. But one thing about this chart that I just want to point out is that that sympathetic output is going to kind of happen before the baroreceptor firing. So that sympathetic output is what will actually cause the heart rate to increase, and AKA cause more stretch. And when we see that, that's whenever the baroreceptors will begin to fire. So this parasympathetic and sympathetic output occurs before those baroreceptors detect it, because baroreceptors detect stretch, these cause stretch. So just make that note in your head. That activation of those nervous systems is what kind of causes the baroreceptors to fire. So question number 2. So now we're going to look at an example of blood pressure decreasing, kind of what we looked at the beginning, but now we're going to look at the actual components of the reflex. So the receptor that we will see go off whenever our blood pressure decreases is, of course, the baroreceptor, what we're talking about today. So the integrating center is, again, what we've talked about multiple times, the cardiovascular control center. And the efferents, the exiting signals, are coming from the sympathetic nervous system. And remember, the sympathetic nervous system innervates all of those different areas, both of the nodes, the contractile cells, and the arterioles and veins. And if you didn't get that last part, it's on the next slide. So the next one is kind of looking at the effectors that we just looked at previously. So what the question 3 is talking about is again, the baroreceptor reflex and the synapses on the inner neurons in the central nervous system. So what we see is that the inner neurons will turn the synapse onto the sympathetic and parasympathetic neurons, leading to that cardiovascular control center response. So the question here is just looking at those targets. We've discussed this twice now. So just this kind of puts it into a chart view on how many the SNS innervates compared to the PSNS. So we've written this down a few times, but just in case you did not get it, this is what we are targeting with PSNS activation and SNS activation from the cardiovascular control center. So moving on to question 4. So now we're looking at increases or decreases or no change. So when blood pressure increases, we haven't looked at an example of a blood pressure increase yet. So what we see is that when blood pressure increases, the baroreceptor firing rate is going to increase as well. And the firing rate of the sensory neurons that link the baroreceptors to the brain will also increase. So blood pressure increases, baroreceptor firing increases, which will decrease, SNS activity, increase PSNS activity. And those sensory neurons, afferent, meaning arrive at the central nervous system, will also increase. All right, so question number 5, to accomplish this sympathetic output, or to accomplish a decrease in blood pressure, sympathetic output from the brain to the cardiovascular targets should decrease. So if we have a decrease in blood pressure, appropriate response to this reflex is decrease in blood pressure. Okay, yeah, so I guess 4, 5, and 6 kind of go together. So this might not make sense since I don't have them on the same slide. But if you have the discussion worksheet, they all kind of flow together. So if we have an increase in blood pressure, the response is to decrease it, to kind of bring it back to normal. So to accomplish that, the sympathetic output should decrease. So going back with that previous one, that increase, PSNS will increase, SNS will decrease. So next, and again, this goes with those previous 2, does the firing rate on the input side of the reflex match the firing rate of the output side? That is no, because that input side is an increase in blood pressure, and that decrease, or that output side is going to be a decrease in SNS activity. So we have an increase in the sensory increase, but a decrease in sympathetic nervous system activity. Sorry, this worksheet's pretty boring. There was like no way to make this interesting. Okay, so if the signal increases in firing rate, but the output does not, does that indicate a link in excitatory or inhibitory neurons? That's going to be inhibitory. Because we have that inhibition effect. So that increase in firing rate that causes that decrease is inhibitory. If it was excitatory, that increase input would cause an increase in output. But we see an increase in input and a decrease in output. So that's why it's inhibitory. And then lastly, we're looking at a case study. So we're looking at patients at a cardio clinic, and one of them has been diagnosed with Wolff-Parkinson-White syndrome, so WPW. What happens with those who have WPW is they have an issue with the electrical conduction in the atrium and ventricles of their heart. So let's look at this one because I kind of break it down. So normally electrical signals, from what we studied last week, start in the SA node, then go through the 2 atrium to the AV node, then down the bundle branches and through the Purkinje fibers to cause the ventricles to contract. So, in a normal electrical signal, the atrium are supposed to depolarize together and the ventricles are supposed to depolarize together. However, those with Wolff-Parkinson-White syndrome, what we see is there's extra conduction in the AV node. And this leads to the ventricles not generating their action potentials at the same time. So one will contract quicker, and that is not good. That's going to cause a lot of issues. So when we look at this on an EKG, this is how you would determine if someone has WPW. What we would see compared to a normal EKG is no dip because those ventricles are kind of contracting together. So here's what a normal EKG would look like. And then someone with WPW, you can see that one ventricle contracts quicker than the other. So that's not shown as well here, but on a real EKG, you can see how one ventricle contracts and then the next ventricle contracts. So normally we have this Q dip, then the R, S. However, here we don't really have that dip. We just have a contraction and then another contraction, which is very, very bad for the body. We're not going to get blood to the correct areas. So this is an issue. So this is kind of like a really severe EKG showing WPW. This is a less severe version. But those kind of points, those pokes on the EKG, two dips there is going to mean WPW. So yeah. Alrighty, so sorry, today's discussion is not that interesting. But luckily, next week we get into spirometry. The respiratory system is my favorite system. So we're gonna look at deep breathing and all of that stuff. So next week is gonna be a lot more interesting. But luckily this week wasn't like too in-depth, so you don't have much to worry about. But yeah, that's all I have for y'all. So I'll stick around for any questions. Sorry, class ended in 21 minutes, but thank y'all so much for coming. And I will see y'all after exam 3 next week. So we will start spirometry.
So are there receptors dilating? Sorry, my brain's just
Yeah, no problem.
No problem. The baroreceptors always switch.
So they will detect stretch. So if the vessel stretches, that's what they're going to detect. If the vessel shrinks, they're also going to detect. Yeah, so they're just going to.
This happens first. So whenever you're stressed and you have a high blood pressure, so whenever you're stressed and have a high blood pressure, it detects that it's small.
Exactly. So it
why
detects
does
that it's not as stretched.
So why does the firing rate decrease? Wouldn't it both increase to the heart? It just detects a smaller section. I was just.
Yep, you're right. You're right. No, so it doesn't detect shrink. It just detects stretch. So that mechanical stretch. So that's
Okay.
why if we have low blood pressure, and so if we have low blood pressure, we're gonna have a more stretched out vessel.
Low blood pressure will stretch.
Yes, so the vessel will be more dilated. So you can think of that inverse increased pressure, decreased volume, or just,
Yes.
Area.
I understand that.
Yeah, so if we have our vessel and it's like this, increased pressure, this is decreased pressure.
Right, so this would cause, this is like gonna cause the sympathetic to go because it's has a low blood pressure.
Exactly. So these baroreceptors will be like, dang, we're, really stretched out compared to like here, they're like tiny guys, they aren't stretched. But since they're stretched wider here, that will cause an increase in SNS activity. So we can, cause that smaller size, and it'll do that by increasing epinephrine.
I
which will
just don't
increase
understand. The only part that I'm confused about is why does that, when it's like low pressure and hot and low blood pressure, why does that decrease the baroreceptor firing rate?
So because they're mechanical receptors, so they're only going, so here we have,
So it's only increased when there's constriction.
exactly,
Okay.
exactly. So whenever they feel that stretch, yes.
You said that the sympathetic and parasympathetic fires before?
Yes, so what happens is the parasympathetic nervous system is going to pick up on, hey, we're feeling faint, like our blood pressure is low, or hey, you're super stressed out. And so the nervous system is going to be first to pick up on that. So it goes nervous system. The nervous system is going to send it to the cardiovascular control center. And then the cardiovascular control center is what's going to cause that increase in heart rate or that decrease in heart rate. And you can think of heart rate and blood pressure as kind of synonymous, or blood volume. So the cardiac control center will be like, hey, we need to increase our heart rate because the nervous system is telling us that, we have low blood pressure or high blood pressure. And so whenever we have that increase in heart rate or that decrease in heart rate, that's going to cause a change in how our vessels are contracting and dilating. So if we have an increased heart rate, the vessels are going to kind of constrict. If we have a decreased heart rate, they're going to kind of widen. So whenever that happens, that's when the baroreceptors are activated. So
So when you say it feels the stretch, you're saying it feels the stretch when they're constricted.
I honestly don't know.
That's why I'm confused.
Yeah.
That's like the only part that's confusing.
Here, let's see, I wrote an extra
Because
note. So
I get that when they're constricted, it's gonna increase parasympathetic.
mhm,
But parasympathetic
yes,
is basically when they're too constricted. That's when that happens.
yes. So that firing rate, whenever we have low blood pressure, is going to decrease. And I think that's that negative feedback loop.
I don't get it at all. I'm just so
Wait.